Why do I feel so heavy now?
Initially, Guinevere feels heavier because the lift is accelerating upwards due to a resultant force. The resultant force on the lift is the tension minus the combined weight, while the resultant force acting on Guinevere is the normal contact force minus her weight. By Newton's second law, the acceleration upwards indicates that there's a resultant force on the lift. This is the same acceleration acting on Guinevere. Guinevere's true weight does not change throughout the motion as her relative distance from the Earth's surface is way smaller compared to the radius of the Earth. This means that the normal contact force on Guinevere is greater than the true weight. Thus, Guinevere feels heavier at the start.
Why do I feel so light now?
Is about to reach the designated floor, the lift has to decelerate. By Newton's second law, the lift experiences a resultant force downwards this time. With no change in the true weight, the resultant force is weight minus tension, as tension is now smaller than the weight. The deceleration by lift is the same deceleration experienced by Guinevere as they are in contact. For Guinevere, the normal contact force is now smaller than her weight, so as to have the same deceleration as the lift. The normal contact force and tension, unlike weight, is able to change in magnitude. The normal contact force being smaller than her weight is what makes Guinevere feel that she is now lighter.
Hi, Daddy.
Hi, daughter.
Why are you home so early?
Where's your girlfriend?
Father, I'm going to play basketball. Do you want to play with me?
No.
He may be your father, but I'm your daddy.
When the ball hits the wall, an inelastic collision occurs. This is because the relative speed of approach of the ball is not equal to the relative speed of separation. During the collision, the total momentum is still conserved. Thus, the initial total momentum is equal to the final total momentum before and after the collision. Contrary to the total momentum, the individual momentum of the ball will change due to the forces exerted on it. There is a drop in kinetic energy as it is lost to the surroundings through heat and sound, and since kinetic energy is equal to half mv squared, velocity is lost when mass remains constant. Since momentum is equal to mass times velocity, the final momentum of the ball will be lower than the initial momentum. Even though the wall experiences a change in momentum as well, the change is unnoticeable because the mass of the wall is significantly greater. When the ball collides with the wall and the ball exert force on each other. Thus, the ball loses momentum while the wall gains momentum.
Step aside. Projectile motion is defined as when an object has a constant velocity in one direction and a negative acceleration in the perpendicular direction. When Tristan shoots the basketball, the ball travels at an angle to the horizontal, and the motion of the ball can be classified into two directions, the horizontal and vertical directions, giving it a resultant velocity. The horizontal velocity of the ball is considered to be constant as there is negligible air resistance. Before the maximum height of the ball, taking up and left to be positive, both the horizontal and vertical velocities are in the positive direction, causing the ball to move up from Tristan's hands and towards the backboard of the hoop. When the ball reaches its maximum height, it still has a positive horizontal velocity, but its vertical velocity has reached zero. This is because of the gravitational force acting on the ball, which gives it a negative vertical acceleration. Hence, the vertical velocity of the ball decreases with time. After the maximum height, the ball falls down towards the hoop, showing that it has a negative vertical velocity, and hence the ball enters the hoop. He shoots! He scores!
Loser.
Don't tell me I'm so sorry. I didn't think Frisbee would fly that far.
I wonder how a frisbee flies.
The curved shape of the frisbee causes air above it to travel at a higher velocity than the air below the frisbee. Thus, according to Bernoulli's principle, pressure above the frisbee will be lower than that below it. Since pressure is defined as normal force acting per unit cross-sectional area, given that the upper and lower areas of the frisbee are equal, this pressure difference results in a net upward force on the frisbee, which is the lift force L. The lift force L opposes gravity. Drag force D is a resistant force on the frisbee perpendicular to the lift force L and acts against the frisbee's movement through the air. The angle at which the frisbee is thrown and the angle of attack theta affects both lift force L and drag force D. The resultant force from the lift force L and drag force D tilts the frisbee, causing air to be deflected downwards.